start the session. All right. Okay. Any other questions before that? Robert is saying that MapR 1.0 became Yarn plus MapReduce 2.0. Right, right. Let's not confuse MapR as a company. There was a company as well with the name called MapR. Okay. Here we are talking about MapReduce component of Hadoop ecosystem. All right. So MapReduce 1.0. All right. So MapReduce 1.0 was broken into two components, or you can say refactored. Refactor is the term which we use in programming to break big function or big component into two small components or multiple small components so that they can be used, reused by in various ways. All right. Did I make sense, Robert? Great. So this is going to be later. All right. All right. So let me break it down. Okay. All right. I'll just take it as a note for myself. And all right. So yes, that's okay. Let me just check which one are you referring. Okay. What's the date today? Okay. Right in June. All right. All right. Good. So earlier, so far, let me just do a quick recap in a minute. So first we discussed that how big data becomes problem to existing tools. Then we tried to solve our basic problem of storage with HDFS. First, we tried to figure out what was the problem with the old form of spaces. Then how does HDFS solves it? And then we discussed how does the computing is distributed using yarn. How do we divide work amongst many machines using yarn? And then and then how to build such a program which can take the benefit of MapReduce. So we're going to go more detailed into MapReduce now. Okay. All right. So we have discussed the problem related to computing on a single machine and how to solve those using multiple machines. And as opposed to building custom program, how MapReduce is better, right? In custom program, you have to do a lot of engineering. There is a lot of chance of failures when you get done work from many machines, and that's where MapReduce comes into play. Okay, all right, good. So this was one example of mapper and reducer for word frequency problem. Okay, all right. So here the mapper, essentially, what is it that we are doing in MapReduce? Okay, it's a programmatic way of grouping the data. All right. As part of the map function, we give out that my data is this, where key is this, and value is this, so that Hadoop will group the data based on the key, and then apply reduce function for all the values for each key. Okay. So essentially, this is how your reduce function is going to look like. Reduce function will get a key in the argument and an array of values. And what are these values? And what is this key? This key is spitted out by map, and this is the value being spitted by the map. All right. So you can see that it is essentially um, it is quite straightforward to do the grouping here. All right. Now let me ask you, I want to take a little digression from my usual route, and I want to take a different example this time. Okay. Where is my, okay, here's my hue. All right. I'm going to take a different data set. And what is this data set about? Okay. So everybody is clear about the this mechanism, or should I repeat once? So we first discussed this approach where one launcher will be dividing the work, but this is too much of custom work. Okay, and interestingly, this is what we did long back ago when we did not have Hadoop kind of system in place. All right, so we have MapReduce. MapReduce is a way of programming. Okay, why do we need a newer way of programming? Because we want to build the code in such a way that instead of moving data, we move the code. Okay, and when you do that, your ways of getting things done change a little bit. So instead of saying give me the data, I will loop over it. Okay, instead of saying that, what we do is we give the function to the system that, hey, here is my function, can you run this function against each section of the data, right? That is the biggest difference. All right, all right. So essentially, instead of asking system to give me all the data, like the way we used to call a function which will iterate over the whole range of data. Okay, instead of that, we create a logic and apply that logic uh, on the big data. Right, let me try to see if I can make it a little more simpler to you. All right, okay, so let's say we have array equals this, some records are there in this array. Okay, and let's say 10,000 records. Okay, now what you want to do is you want to square this every element. Okay, one way is you could say, I'm writing kind of a pseudocode. One way is you say for x in array, okay, we say we say let's say we're just printing it. Okay, we say print x into x. Correct. All right, is this clear to everyone, this approach? Okay, so what is it that we are doing here? We are given a big array of data and we are running our function which will read one element at a time and print the data. The Do you see anything wrong with this approach? So this approach is quite valid, but we cannot process the data which can't fit into the memory, right? And this logic could be quite complex, and you may not be able to break it into parallel system. Okay, let's say now let me break it down a little bit. Let me put a little puzzle over here. What if you have um, you have mm, dual core machine? What will you do to optimize it? Meaning you have two processors on your machine. Do you think if one of the processor worked from 1 to 5,000 element, and for rest of the element the second processor worked, do you think that this could have worked faster? Right, if we had two processors. Okay, two processors. I'm just taking two processors. So will it be faster? But question is that if you had two processors, dividing this for loop is impossible automatically. Correct? You will have to rewrite the logic. And that's where the whole distributed bit comes into play. All right. So now imagine this. I mean, we have been doing MapReduce far, far before Hadoop. Okay. So, I mean, I have used MapReduce in Perl long back in 2002, 2003. And that was for a different reason, for simplifying the logic for multiple machines, for multiple cores, actually. I mean, for parallelizing the activities. Now, imagine that instead of writing our logic this way, okay, let's say there is a map reduce mechanism in the programming language itself. There is a library which executes array.map and my function. Okay, and let's say we have to define our function. I'm trying to keep the code really simple. I'll just write function my func, and it essentially, okay, my func, and here we are saying this is not it's a mix of JavaScript and Python, so don't worry. And I'm trying to write a simple pseudocode. Okay, and here I say an element x, and I say return x into x. Okay, now imagine this way. So by the way, Python provides a function called map. Okay, what does that map do is it applies a function on every element of the array. So if you look at this map function, it's nothing but a big for loop. Okay. Uh, all right. So 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 basically, instead of we iterating, instead of we writing a logic to iterate over an array, the programming language construct called map is iterating over an array, and your function is being applied on every element of an array. Okay? Your function is being applied on every element of array so that this new function, the new array would be, a new array would contain squares. Okay, now there is a shift of paradigm here. Now, in if tomorrow somebody comes with a map function, some programming language comes with a map function which internally handles the load, which internally divides the work into many processor, your function does not need to be changed. Do you notice that? So all you have to do is change the map function, and change the implementation of map function. Correct? Your function, my func, this logic will remain as such, irrespective of how the how do you essentially iterate over the elements. Okay, this map function could be uh, using many processors. This map function could be doing the threads, or it is using many processes on the same machine. It's none of your concern. Okay, you are more focused in writing a brilliant function called myfunc, right? It's a separation of concern. The iteration work, the work of going over elements, you have handed over to map. Okay, earlier you were using a for loop, correct? Okay, is this the difference in approaches clear to you? That's right, Raul. That's exactly. So map function would take care of breaking and processing the code on different processors. So here I'm talking in general the distributed computing. And this um, this is a general way. Be it we have used it in game programmings, we have used it in say Spark. So it's a general. Here I'm talking in a very general way, the distributed computing, or sometimes we call it multi-core computing, and parallel computing, parallel processing is the name of similar thing. Okay. All right, just a second. Question from Kanan is, so map is the function used to store the array value in another variable. So actually map is not storing. Okay, let me just change this declaration a little bit to describe. If I have to do, let's say the most rudimentary implementation of function would be function, let's say map. Internally this would be I'm saying this is the hypothetical hypothetical implementation. Anything starting starting with hash means it's a comment. Okay, so it's a hypothetical implementation I'm trying to describe here. Okay, it's taking some array as argument and some func as the another argument. So I'm saying a simple implementation could be that for x in array, okay, and let's say we have created new array, some a new array equals to element, and we are saying new array dot append, call the func, okay, func, and then we are saying x. Okay, so here we are passing, the most important part is we are passing the function as an argument. Okay, that's something unusual when it comes to this, but we are passing the function in an argument. This way it makes it possible to, so okay, so this part what I've coded just now, what it does is it takes the function handle which you have passed and the array, it iterates over the array and creates a new array, and of course at the end of it it returns new array. Now this is kind of a hypothetical implementation inside the system. Okay, so this is what is the part of these frameworks. This implementation of map and all other related similar functions is the part of MapReduce framework, Spark framework, and other systems. Okay, right now here in this particular implementation, it's doing nothing. It's not iterating over multiple machines. It's doing only a single machine. Okay, we could have done this way, that we find the length of this array, create two threads, one thread runs on one processor and other thread runs on another processor, and then we start it. So so there could be many implementations of map, and every framework is competing in getting this implementation fastest. Okay, map reduces, sort, and there are many more functions as we'll explore as we go further. Everybody is trying to improve this distribution of work and execution of distributed work. All right, so okay, let me answer two questions. Balwinder's question is, does map function call internally, calls reduce as well as returns ultimate output? No, here the map function is not internally calling reduce. Okay, but the map reduce system will call our both mapper and reducer. Okay, so here we are returning an array. All right. Next question from Akash, but it's same as iteration through the array and calling my functions every time. Just we have used a built-in function that is map. Yes, in this implementation, the one which I have done here, it's not efficient. It may be slightly slower than our for loop, but if it is done correctly, it could become really, really fast. Okay. All right. So now, the point I was trying to do is the difference between these two approaches. One, where we are iterating over the full data, we are iterating over the full data one at a time. And the second approach in which we are letting system iterate and do the processing of our choice. Okay, and how do we define our choice? We have created our function and handed over this function as the function here. We have handed over to the system. Okay, so coming back to our MapReduce again, same thing we are going to do in this MapReduce of okay, in this MapReduce where there is a input data and we want to process it. We do not want to iterate ourselves. Okay, we because the data is distributed, we do not anyway have any control over which record is on which machine. We do not have a choice. Okay, also one point I forgot to make: when we sift from first approach to second approach, there are limitations. There are limitations. You cannot do you do not have a control over the sequence. Okay, you do not have a control over the sequence. Therefore there are many things that you cannot do using MapReduce. Okay, using this kind of approach where we are delegating the work of iteration to the system, because system, whether MapReduce, Hadoop MapReduce, or Spark, or other systems, all of those systems will essentially have their own way. So internally, we could here the iteration could be happening from backwards to forwards, or say three threads working on one third data each parallelly. So you don't have a control over the sequence. So you cannot convert a problem like Fibonacci series. Okay, so you cannot convert certain logic into this kind of a logic. Okay, you cannot convert every for loop into a map function. Okay, because you don't have a control over the sequence, because you have given up that control in order for efficiency. You have told the system that, hey, we don't care about in which order you process the data. We do not care whether you process the data from beginning, from end, or you process using many multiple parallel processes on many machine. It doesn't matter to us. As long as our data get processed, we are fine. Okay, and here is the way our every element need to be changed. Okay, so this is how. So you will see that as we go more and more, not every logic could be converted into MapReduce. Think about Fibonacci series. What is a Fibonacci series? Fibonacci series starts with 1. Okay, first two elements are 1 and 1. Third element is the summation of the first two, which is this. Next element is again summation of these two elements, which is 3. Now this is 5, and then 8, and then 8 plus 5 is 13, and so on, right? So this is Fibonacci series. So if you notice in Fibonacci series, to generate the next number, you need previous two numbers. Therefore, therefore, distributing such a work is going to be an uphill task. It's impossible to do it parallelly, because next step has to wait for previous step, and previous step has to wait for previous step, and so on. Therefore, a problem like Fibonacci series can only happen at its own slow pace using a single thread. Okay, so therefore I'll show you the kind of functional, right? So I'll say this is my Fibonacci series, and I'll say for okay, previous equals 0, and for, let's say I want to print up to n for I okay, for x in 1 to n. Okay, and I'll say previous plus equals x and print previous. So something of this sort. I'm not sure if this is the correct logic. Okay. So I'll say, yeah, okay, I'll say, how would I say? Previous plus equals to x. Okay, so this is how it's going to be. Yeah, it's actually missing the first one because it'll print 1, 2, and then 3, and so on. Okay, so I think this will do. All right, so you can see that I think this should do. All right, okay, right. So now you can see that where previous is being computed from the the next value is being computed from the previous value. Therefore, this is not possible to distribute. So Rawls' point is that MapReduce cannot be used used at the places where there is a dependency in the data. So dependency of the sort very linear dependency, as in next element computation requires previous element. But if you say that my overall computation requires computation of first half of an array and then second half of an array and then summation of the two, those kind of works can be broken down into maps and reduces. All right. Okay. So, did I make any sense? If it's not clear, I would love to explain again. This is important. Okay. This is important. All right. Anybody else wants me to repeat once more? Because this particular concept is valid for lots of things as you will study further, whether to do with parallel computing or to do with say Spark, the uh, Spark parallel computing and MapReduce from Hadoop, and there are a few more parallel systems which actually use the same mechanism. All right, you will understand it as we go further. All right. So here, all I was trying to say is there are two approaches to square every element of an array. One is very simple and straightforward, that this is something which we have been doing for quite some time. Okay. And the way we were doing is, let's say we want to square all the elements of an array. All we will do is multiply the element by itself and iterate by over the array, right? So we go over the array ourselves, our code, we write the logic saying go from one element to another and so on. The problem with this kind of computing is it's very difficult to break down into multi-thread, multiple machine, and so on. Let's say, because when we are doing the computation of this squaring of every element, it is possible to do it, divide the work amongst many processors, and you breaking this down, this for loop is almost impossible. Okay. Therefore, therefore, one of the very successful ways is let the system iterate over let the system iterate over the data, and you concern yourself only for processing every element or processing the data. You don't iterate. You leave the iteration part to the system. Okay? Similar to event saying, hey, I don't want to execute it now. When there is a data, let it be executed. So that's where the idea of a map came from. So you could write the map function. You could call map function from a programming language. Perl has it, and Python has it, and all these newer systems have it. So how does it work? You write your function, whatever logic you want to apply on every element, whatever logic you want to apply on every element of the array, you write it in a function and then call the map function. Say map array. Array is the data, and the function is your code. So you are handing over the reference to the data and reference to your function. Now this map function internally could do many magical things. One magical thing it could do is it could use many threads. Okay, in one thread, let's say it is using two threads, and in one thread it's executing your function for elements from 0th to say 5000, and in the second thread it's executing, it's running your function. So you have handed over your function. Okay, you are saying to the map function that, hey, it doesn't matter to me how and where you run this function, as long as it's run on the elements of my array. Okay, whether you run it on one processor, other processor, you run it 1,000 times or 1,000,000 times, it doesn't matter to me. Okay, as long as I get this result. So you hand over the code and the reference to the data, reference to the code and reference to the data to the system. And this implementation of map function is something all of these, whether Hadoop MapReduce or Spark MapReduce, they take pride in. They do the chest thumping that, hey, my map implementation is faster than yours. Okay, so here probably this is the slowest map implementation I have done here. Here what I'm doing is I'm taking two arguments array. One is array and other is a function. I'm just iterating over it. Okay, so I can't chest thump for my map implementation. Okay. Okay, this Fibonacci series is actually wrong. Okay, so I was trying to explain here is that syst problems like Fibonacci series, okay, I could say previous one and previous two, okay, and then say 0, 1, while, okay, while, okay, I'm just writing some pseudocode, loop until n, or loop n times, okay, and we say that next equals to previous one plus previous two, okay, and print next. Previous one equals to previous two, and previous two equals to next. Okay, so this is something just okay. Or you can say that here next, okay, while next is less than n. Okay, so the purpose of this example was that the things like Fibonacci series, and what's a Fibonacci series? From left to right, you keep on summing up previous two values and generating next two values. 1 plus 1 is 2, 2 plus 1 is 3, and 3 plus 2 is 5, and 5 plus 3 is 8. Okay? Right? In this kind of cases where your next computation depends on previous, you really cannot distribute it. You really cannot send it to multiple computers. Okay? All right. Now let's move on to our main discussion. Let's talk about few more examples. One thing we have talked earlier about word count, and then we will go more and more detailed and then try to do more things. Okay? All right, so I hope everybody is with me so far. Great, great. All right, all right. I'm really happy that everybody got the idea of mapper. This is a very generic way of doing the mapper and reducer, and I wanted to introduce you to this idea before getting into MapReduce because this idea is more generic than the MapReduce which we are going to read in study in the Hadoop MapReduce. Okay. All right, awesome. Okay, so let's move. So let's take the case of mapper reducer of word frequency. So we only talked about mapper just now. Now there is another thing called reduce. When you have to convert, when you have to convert multiple values into single one, you generally have to code your own method. Okay, and that's called the reduce. Okay, so I'll try to explain again. So in case of Hadoop MapReduce, you write two functions. One that need to be applied on every element of an input. And before you start your MapReduce logic, you always start from the data. What is the data that you're trying to process? In this case, we are given a big text file containing some words, and we have to do certain counting. And the map function, whatever we write, is going to be applied on every line of this file. Our map function is going to be applied on every line, meaning whatever function we create is going to be called equal to the number of lines this file has. Okay, if there are 5,000 lines, our map function, whatever function we write, so this is, you can say, my mapper function. Okay, you can, I've just written mapper, don't confuse it with, okay, this is my reducer function. Okay, here I'm not able to modify it. Yeah, so I can say that it's a reducer, my reducer function. It's just any name we can write. Okay, so here we could say convert to words, and second one we could say summing up. Okay, so here is the idea. So you're given a big file, and what you want to do is you want to count words in it. So you write a function, and you know that whatever function you write, it's going to be called on every line. So what you do is you basically write a function which reads every line at a time and then convert every line into key value. The expectation, the Hadoop's MapReduce expect that you will write a function that will return a key and the value, because Hadoop's MapReduce will sort the data, whatever output your function gives, not only it's going to collect it from all the machines, but it will also order the data. If you're providing the reducer logic, then it will order the data and then call the reduce method. Okay. So Hadoop's map reduce, one, it does function like normal system. It also provides something called reducer. If you mention reducer, then what it does is it will order the data provided by your mapper, and then it will combine, it will group the data, group all the keys. So let me take a step back. So Hadoop MapReduce contains the reduce aspect as well. Here in this example, we had only talked about mapper phase. Okay. So here in MapReduce, okay, the output of mapper, which is like new array, is going to be ordered by Hadoop and then grouped. Ordered and grouped by the same key, and also it can be different keys. Ordering and grouping could be different keys. Okay. So if you have let's say the input data sare saga, it'll get converted. Let's say you wrote a logic which goes through every word in a line. Okay, this is a line. Okay, and every word in a line is getting converted into key and the value this way. Okay. Now, what will Hadoop do? Hadoop will not only execute your mapper function, Hadoop will take the output of the mapper and feed it to the reducer. Okay. So we discussed only up to here that it will first take your mapper function, execute over every line. And remember, if this file is located in HDFS, then this function then this file which is located in HDFS would be spread across many machines. Therefore, you are never sure whether the mapper function is going to be executed on one machine, two machines, or three machines. You can only figure that out by looking at how many blocks of data you have. Okay? So on every line, your function gets called, your function, whatever it gives out, that data gets sorted. And the criteria for sorting is provided by your code. Your code provides the key and the value, and that's the only reason it needs to provide, because Hadoop needs to sort data and group it. And after grouping, it hands over each group to your reducer. It calls your reducer for every group, and whatever is the result, it saves back in the HDFS. So this is HDFS. So this is HDFS. Okay. And this is a little really small HDFS. Okay. Let me try to duplicate this slide. Okay. All right. So these are the two parts I'm going to discuss. I'm further breaking it down so that it becomes easier. All right. So your mapper function is first called on every line of the input data, and it can produce anything. Okay, just that it has to produce some key and the value in the format. Not only. All right, Raul, I'll come to that answer. Okay, that's a good question. All right, so First is that first need to we need to understand is whatever mapper function you write is going to be called on every machine. And afterwards, if there is a reducer phase, meaning you have specified a reducer, you want to combine your data, then it's optional actually. Okay. So if you don't want to combine or do anything, you're free to just process the data using mapper. Now your question would be, what's the point of running mapper? Okay. Is it only for very complex data that's not fitting into RAM? No, that's just one way. It also, if the data is distributed across many machines, if the data is distributed across many machines, then this function is going to be called on many machines, which means many hard disks or many drives are going to be used parallelly. And therefore, the pace at which the mapper is going to be called on every line of this file is going to be really, really good. Okay? Therefore, even a mapper without reducer makes sense. Even if we are not using Hadoop for sorting or doing any kind of grouping, still sometimes the it makes a lot of sense. Okay, you will see as we go further. Let us say you have thousands of files. Okay, and all of these files need to be encrypted. Okay, so you would like to write a function which takes one file at a time and encrypt the file. Okay, because encryption takes a lot of processing. Therefore, you would like to do the encryption over many machines. So you can see that you can use the mapper in many ways. I'll go into the reducer a little while later. So there could be many use cases. Let's say you are at LinkedIn and there are profile pictures of all the people. Now, what you want to do is you want to go over the profile picture and figure out parallelly, or you want to translate the profile picture into say 100 by 100 square size. You want to pre-prepare that. So what will you do is you will prepare the input data such that on every image your logic gets called, and that logic will essentially write back to HDFS the new file that contains 100 by 100 pixel. Okay, so you can see that it gives you enormous amount of power. You get many processors to process the data, many memories to hold the data in the memory, and many hard disk in parallel which will read the data from the disk without you having to bother about it. Okay, now we will talk about how to process different kind of input files. Input files could be a zip file, tar file, a folder, or input file could be combination of input file could be a audio file, movie file, or a geographical data. Okay, here we are only taking the case of a text file. All right, so I hope I'm able to generate the interest here. That's correct, Anil. That's a very good point. Yes, input to the mapper function is going to be defined by the user. We will define a kind of input data set type. We will say that please read this HDFS file using this reader and call our mapper function. That will be the part of our MapReduce job. As part of the MapReduce job, we provide these specifications to Hadoop that, hey, here is my input data. Here is my input data. It is in the format of JPG, or it's a folder that contains many JPG, and we want every record in this manner. So there are many input splits or many input formats. Okay, we'll go into input formats gradually. Okay, awesome, great. Is everybody with me, or have I uh, gone into my own direction? All right. All right. That's correct, Balvinder. It can do so. You can save the output. This output goes to HDFS back. Okay. There could be many use cases. All right. All right. So we will take few more use cases as we go forward, and then we will talk about. So now the other part is that if the mapper is being executed on many machines, it could be saving data parallelly to many machines in order to do certain processing. Okay. So I mean, let me try to draw a diagram so that everybody is with me. Okay. Imagine this. Imagine this that you have a huge corpus of images. Okay, you have a huge corpus of images. These are images. These are profile pictures of people. Okay, so let's say we call it directory of profile pictures as DFS. Okay, and what you want to do is you want to maybe convert these into exact size, say this size. Okay, so you will write, you will basically write your mapper code, and your mapper code will get executed. Your mapper code as in convert image into 100 by 100 pixels. Okay, and let's say this logic you have written, this is your mapper code. Okay, your this is, let's say, mapper code. So this might get executed on many machines. Okay, and when we're talking about this, it could be that up to here it's on one machine, up to here on this another machine. So your data, these two images will be fed to this, these three images will fed to the same logic, and these four images will be fed to this, and at the same time the data will be saved into your output HDFS folder. Okay, output HDFS folder. Good. So this is an example where there is no reducer, only mapper. Okay. The example of only mapper, not reducer. And only mapper is also quite useful. Okay, whenever we call MapReduce, we think that mapper cannot be segregated and we always have to write key value, and this and that. No, you could write directly a file to the HDFS without doing the key value. Okay, so everybody with me on this? I'm actually quite afraid that I might be digressing a little too much, but yeah. All right. So these are the examples. What I've just taken are essentially a good example. Okay. So example of only mapper. Okay. So it could be used, the mapper reducer paradigm could be used in far more ways. Okay, so only mapper could be used in many ways, but the problem occurs when you have to also do certain processing. Let's say, let's say what you want to do is you want to count the words. If you have to count the words, you have to group the words, right? You have to group the words and sum up the counts and then figure it out whether how many words are there or not, right? If you have to find the frequency table, meaning which word has occurred how many times, then you would have to go one step further. Then you will require the reduce phase of the map reduce as well. All right, and that's what we have here. So when you have to do the work which involves combining data, then you have to come up with a strategy to combine. And the only way of combining data that MapReduce provides us is by grouping it. Okay, is by grouping it. So it's up to you on what basis do you want to group the data. Okay, here we are trying to group the data based on the word, right? And then on the group, your reduce function will get applied. Reduce function and the map function is provided by you. The location, the location of, uh, the location of, just a second, what happened to this guy? Okay, okay, the location of the input file, input data, in what format need to be, your data need to be processed. In our case, we are processing text input format. All of that is provided by you. Okay, so coming back to the point again, here your mapper decides on what basis the data need to be grouped, and reduce decides on what basis the group needs to be, the grouped values needs to be combined together. All right. So, so if there are a million unique words in your input text, your reducer function is going to be called a million times. If there are a billion lines in the input text, your mapper function is going to be called a billion times. Okay, for every line, the mapper function is going to be called, and your mapper function is deciding and telling Hadoop that, hey, could you please group the data based on this key? And then Hadoop will internally distribute the work of grouping the data. Grouping requires sorting. And once it has done the grouping, it will hand over the work to reducer. All right. Now, a question from somebody was how it happens parallelly on many machines. I'll come back to that in a while. Okay. Now, let's understand that this processing, this conversion of every line into key value or execution of your function would happen parallelly like this. Node 1 map function get executed. It gives sorted data, gives the key value, and sorting happens on every machine. Okay, again, the big doubt, on what basis and how will it sort? The sorting happens on every node. Okay, sorting happens on every node, and then once the sorting has been done, the merging happens on a single node here. Okay, we'll see how merging can happen on many nodes, but right now if there is a single reducer, there can be multiple reducer, but right now in this case there is a single reducer. So we let every individual node, whatever logic we have written, which converts input line into text file, input line from the text file into key value, where key is the word and value is some a number, right? So that sorting happens on every node. Sorting of your words which your mapper has given out. And then merging and grouping is happening here. So in this diagram, you can see at stage 1, you have sa, res, ga. At stage 1, you have Sare on the second computer. These are two different computers. And the map function contains exactly same logic which you have handed over to Hadoop. Okay, so this is how it looks like. So your mapper function converted this at the stage number 2. This is what you have. Okay, here Savan, Savan, Ravan, Savan, and Gavan. Okay, and the same thing is happening on the second node parallelly. And on first node, the ordering would happen, which means this would be ordered Ga, Re, Sa, and Sa. Similarly, on third node, or in the second node at the stage 3, the data is sorted. And once it's sorted, as we have already seen, that merging the sorted data and still remain sorted is very easy. It's pretty straightforward. If you have two arrays which contains the data which is ordered, it's very simple. You stand in front of the queue and take the front two and compare them, take the smaller one, and then keep on doing it again and again. That's what happens in case of merge. Afterwards, after the data is merged together, okay, the grouping is very straightforward, and grouping happens here. And then for every group, grouping means all those all those records in which are for the same words having the same key, their values are brought together as a big array, and that's fed to the reducer. That's fed to the reducer, and then the your function, the whatever reducer code you have written, which basically combines these values together, or does something to combine or or process this group of values for each key. That's the reducer, and the output of the reducer goes back to the HDFS. This is where the data gets saved to the HDFS. All right. The same thing. Anil's question is, how is recursive computation handled in MapReduce? Example, if you want to run recursive algorithm on graph data. Okay, give me a little bit more example. So let's say what you want to do is, I think I understand partially what you're trying to do. Okay, so let me try to understand what do you mean by that. Because converting your logic into MapReduce is kind of, requires a little bit than more work. Okay, so you can, yeah. So let's say what you want to do is you have graph of data, right? Let's say you have graph of data, and I'm just drawing some graph, okay? What you want to do is you want to count number of nodes, number of children below every node, right? Let's say here this contains two children, these are two, it contains 2 plus 1, 3, and so on, right? That's what you are trying to do. This kind of computation is quite difficult to do in case of MapReduce. Okay, because unless you break down this problem into a grouping, you group the data, do the computation. Unless you do that, having the recursive one is pretty tough. Okay, it's pretty tough, and you will see that. That's why the newer systems like Giraffe and GraphX has been designed. Okay, great question. Right now on this example, merge is happening in second. I'll come back to the multiple node in a minute. Now, the same thing, whatever I have described just now, is being shown in this diagram as well. What's happening here? This is the data this is the data loaded from HDFS. Okay, there's a slight difference between HDFS block and split zero, split input split. We'll talk about it. So data after getting loaded from HDFS is called split. So there are three data blocks. Input block zero, we call it a split right now. So there are three data blocks parallelly on three machines. And then on every record from each block, your mapper function is called. Your mapper function is called on every record. Although the process is initialized only once, but the method is called many times on every record, because this split zero means it's a data set containing records. In our case, which is word count, this is basically a section of file. It's a part of the file which contains many lines. For every part of the file on every block or on every node, your whole process is only initialized once, otherwise could be very big headache, right? On every node for every part, the process is initialized only once, while your mapper method is called many times. Or you can say that your mapper method called against every record of this input split. Or you can say the HDFS block, or whatever you want to call it. So we'll talk about what's the difference between HDFS block and split later. So right now you just think of it as it's a set of records. In our case, it's a number of lines. Okay, so the mapper function converts that every line into certain key and value. Okay, and then here the sorting happens and the data gets copied after sorting onto some other node and merged. After merging means same key could be here, same key could be here, same key could be here. When they're brought together, there are, let's say, we can say, let me just put something here. Let's say the is occurring 5 times here. Let's say the is occurring 2 times here, and the is occurring 1 time here, right? Right. So, so this, after getting ordered, when they are merged together, all those will be brought together because the data is sorted, correct? Here at this point, and then the merging will happen. After merging, then the reduce will be called on every single key. Okay, on every single group of the values for each key. And the result, whatever your reduce function produces, goes to HDFS. Now the question is, what happens in case of multiple nodes? Okay, I'll try to describe here. This is a little better and cleaner diagram. Okay, so is this clear to everyone? Everybody is comfortable with this mechanism? Right now, the merging is happening on a single machine. We'll go into multiple machines in a minute. Is there any doubt at this point, please? I would like to, clear the doubt before I jump into more details. This mechanics, understanding this mechanics is important because it gives you this perception of things, perception of what is the machinery, and therefore it helps help you organize your logic. Okay, I was actually wondering, so somebody was running 5 virtual machines on a single computer, and it has a single hard disk, and he was doing certain computation on MapReduce. So basically, it was a single hard disk, and his data was huge. So I was saying that if you had like 5 hard disks on the same machine, it could have been better, right? Or if you had 5 different machines in parallel, it could have been even better because you are not utilizing the disk read speeds. Okay, and because He hasn't gone through the process of understanding MapReduce. That's why his doubts were quite high. Okay, and and once you go through this process, you will be able to visualize the problem statement in a more efficient way. Okay, that's the reason I'm going through these details. All right, now let me try to explain here. Okay, so let us say that you realize that your single reduce node, because merging was happening on that single reduce node, and on the same node there are millions of groups that on which the reduce function gets called. So sometimes you would like to divide the work of a single reducer into multiple, and here is the magic. So what happens is that just after the map, key values are split into multiple buckets. And how many buckets? These buckets are equal to the reducers. If you plan, this number of reducers is clearly your choice. You decide how many reducers do you want. Okay? And your question would be, how should I decide? Generally, when you look at the statistics, when you run your MapReduce code, when you look at the statistics and you see that there's a lot of time being spent in the computation on reduced node. Okay, a lot of time is being spent on the reduced node. In those cases, you generally would prefer to have multiple reducers. Okay, although generally it's a hit and trial to decide how many reduce node you want, reducer node do you want. So here we are talking about two reducer nodes. Here we are talking about two reducer node. So just after the data has been spit out by your map function, the certain key go into first bucket and certain key go into second bucket. Similarly, the same thing is happening on every node. Now, first bucket is taken to the first reducer, second bucket is taken to the second reducer. First bucket goes to first reducer, second bucket goes to the second reducer. The important part to note is, if let us say your key called XYZ, let's say you're putting XYZ here, XYZ will also be kept in this machine. Okay? If the same key generated on many different nodes, they should always go into the same bucket. Otherwise, same group will be on many machines. Therefore, it is ensured by Hadoop that same key should always go to same machine. Okay? All right. So what exactly is happening? So there was a big file which was broken down into three blocks of data. Block 0, block 1, block 2. You handed over your logic, which basically converts a big line into one word per line. Word is your key, value is the one. That's what your mapper is doing. Your map function gets executed against every line in the input file. Okay, so 10 lines here, 10 lines here, 50 lines here. So your function gets executed 50 plus 10 plus 10 times. 70 times. If there are a million lines here, a million lines here, a million lines here, your function is going to be called 3 million times. Okay, and your function might convert every line into say 20 words on average. So there will be 20 million keys produced after this. Okay, the important part to understand here is some of the keys of the mapper go to the first bucket, some of the keys go to the second bucket. And now your next question would be, on what basis are we dividing it? Generally, there is a mechanism called hashing. Okay, on the mechanism called hashing. Okay, so first bucket, these two buckets are provided to you the way there are multiple dustbins in your house. So you put certain kind of garbage in one, certain kind of garbage in another, and then some of the, so these buckets are taken to different places. In the same way, the output of the mapper is taken to different places. But you have to ensure that same things which belong together should be kept in the same bucket. But generally, this is taken care by hashing function. Here, the magic, the splitting is happening based on a hashing function. And how does the hashing function generally work? Let's say, so hashing function could be as simple as you could create a simple hashing function. Okay, I'll show you one hashing function. Let's say which if first character is between 0 and first character is between A and J, return 0. 0 means put it in the first bucket. Otherwise, return 1, right? We will write this hashing function later on. We call it partitioner. Okay? We call it partitioner. Okay. And what is a hashing function? Generally, people ask. Hashing function is converting a string into a number. Okay, it's not we're not talking here about checksum. Okay, we are not talking about checksum. So a string gets converted into a number, and you can say hash code. Okay, so it's a standard mathematical way of creating hash code. uh, I mean, converting a big string into a number. Okay, there could be many ways. You could create your own sum up all ASCII values of a string and then divide by 5,000. Okay, something like this. Could be arbitrary. Every language provides a hashing code, almost every, not every. Okay, so hash code is a good way to break down any string or convert any string into a big number. Okay, so also please note that multiple strings could, multiple different strings could result in same hash code. Okay, so that's what decides, on that basis of hash code is decided to whether to keep it in first one, second one, or third one. All right, so generally the logic is convert the convert the string or binary data into a number, and then divide that number by divide that number by number of reducers. Okay, divide the number of reducers, and based on remainder we put in the output. I'll describe this. So let's say the hash code is 20. Okay, so hash code is 20. It goes like if hash code is 0, it goes here. Hash code is 1, it goes here. If hash code is 3, it goes 0 1 0, right? So that's how the remainder works. So 3 divided by 2 is 1. Remainder is 1, therefore it goes here. Similarly, Okay, so 3 divided by 2 is 1, and therefore 1 is here, 0 is this one. So basically, whenever we have a huge number of people that need to be allotted in a round robin fashion, certain resources, we generally divide, uh, div- uh, do the percentage. Okay, so divide a big number by target buckets, divide the input number by target buckets, and whatever comes out as the remainder, we put the particular value in that bucket. Okay, so basically the key, when it get hash code is generated, it'll be a huge number. And that huge number, if we need to decide whether that huge number goes to first bucket, second bucket, or third bucket, so the quick thing would be divide that number by number of buckets, and whatever is the remainder, because remainder will always be lesser than number of buckets, right? If if the value is even, it'll be the remainder will be 0. If the value is odd, the remainder will be 1, right? So remainder will always be lesser than number of buckets, or equal to lesser than number of buckets, and therefore we the way Hadoop MapReduce does is, first it converts the input key into a hash code, which is a big number, and then compute the remainder by dividing that big number by buckets. So let's say hash code is 1000. 1000 divided by 2, the remainder is 0, therefore it gets to the first one. Had the remainder been 1, let's say 37, 37 is the hash code generated by the internal library for the key, and therefore the 37 will go to the second bucket. So in this manner, we generally divide the work into uniform. If you have been into NCC or any uh, kind of a kind of initial army filing. So what you do is you ask the candidates to call their number from 0, 1 to 0, 1, 2, and then you divide they ask all the candidates who have shouted 0 into to come to one side, who shouted 1 to come to another, and who shouted 2 to come to another. In the same way, all the keys will shout their will be converted into 0, these two buckets, and will be put accordingly. So some keys are kept in 0, some keys are kept in second bucket, or we can one bucket, okay, because they are named after 0 and 1. All right, no worries. So when you have a lot of keys output of your mapper, some of the keys are put in first bucket, some are kept in second, and it is made sure that equal number of keys go into both the buckets, as well as it is made sure the same key from first node and same key from second node always end up in the same reducer. And it is ensured by having a definite function to divide or to distribute the keys into reducers. Okay. A question from Raul. A question. Okay, I missed two, three questions. Okay. All right. Let me take the question after break. I think you all get a chance to go through the questions before it get answered. Okay. All right. So let's take a break. All right. And also, don't worry about whether it's getting delayed or not. I will make sure that whatever needs more attention, I'll pay more attention to it. Okay. For now, let's take a break for 10 minutes. Okay? Break for 10 minutes and back by 9:45. All right, so I'm back. Should we start now? Yes. So should we start? Great, great. All right, here we go. Okay, there are a few things I have not discussed yet. Okay, where are we? Okay, all right. There are three, four questions that need to be answered, and those are good questions. First question was from Ajay. Does framework decide which key bucket should go to? Yes, which key should go to which bucket is decided by the framework, and each bucket is designated to go to a particular reduce node. So each bucket actually is supposed to go to every node. All right. So mapper keeps on executing on every record from input is played, and then every record gets converted into key values. The data gets sorted based on the key provided by the mapper, and then the the output after sorting goes to either first bucket or second bucket. So that way. All right, and then once it gets copied, it gets merged here and then grouped together, and then reduce is called on every group. And the result of the reduce is saved in HDFS. Good. So I hope that answers your question. Now, next question is it true that map is responsible for sort? No, not really. Map just gives out the key value. So map just gives out key values. Your logic of map would not contain any logic related to sorting. Okay? The output of map gets sorted by the framework, and reduce is responsible for merge. Yes. Reduce is just responsible for merging the list of values together. Okay? And there is no intermediate function other than MapReduce. There are. There will be something called partitioner which can decide which key should go to which bucket. Will be a function called combiner which would try to combine value on the same node and so on. Okay, so there will be that kind of situation. Okay, so there will be a combiner, partitioner, input split. So other than these two, what you provide, one will be input format that you will have to provide, and then you will have to provide number of reducers, and you will have to provide you will have to next thing you will have to provide is mapper logic, a mapper code, reducer code. Okay, and next would be the okay, so mapper logic, reducer logic, output folder, and combiner logic, and partitioner logic. Okay, then we'll also discuss how because there are two things happening. One is sorting, another is grouping. So we can also make that separate. That's a separate thing. So input format is optional. Okay, by default text. If you don't provide this, number of reducers optional. By default, it's one. Mapper logic is not optional. Okay, and reducer code is optional. If you don't provide reducer code and turn off the sorting, nothing gets done. Output folder is not optional. Okay, it has to be provided. Combiner logic is optional. Partitioner logic is optional. Okay, good. So we'll talk about all of these parts that we pass to MapReduce. Question from Raul is, how are output files part 0 and part 1 merged to combine the reduce aggregator? Quick answer is not merged. Okay, the files are not merged. These, you will see the when we run this logic, there'll be two files, part 0 and part 1, and therefore it's asking for output folder. Okay, in this output folder it'll create two files, part 0000 and part 0001. Okay, so basically combining the output aggregated data is generally not required. Almost every function in Hadoop ecosystem works on a folder, be it Hive, be it Pig, or be it say MapReduce, where we are providing the input file. We forgot the input file. Okay, we forgot the input file. Input file need to be provided. It's mandatory. Okay, input file slash folder. Okay, so these 8 things is what you can provide, and there are a few more things we will understand as we go forward. So the next phase of output of something can be kept in a single folder. Sorry, generally you do not merge the output generated by reducer if the data is really big. Okay, if data is small, you can use any command, say Hadoop cat, and use the Unix command to concatenate and put it back. Okay, generally almost everything accepts data either from file or a folder. If it's from folder, all the files from that folder are concatenated together for the processing. Okay, great question. Another question from Ajay. For example, if we have 40 gigabytes of data, of which 200 gigabyte belong to key A, 100 gigabyte belongs to B, and other 100 gigabyte belongs to C. Okay, in this case, if we have two reduced tasks, it would be better to send B and C to one reducer and A to another reducer. Great. This is what is decided by something called partitioner. Okay, we can write our logic to say that send all the data related to key A to bucket 0. Okay, so in case of A we say bucket 0. Okay, B we say bucket 1. Okay, we will see how it happens, and in case of C also we say bucket 1. Okay, so this way we can code the partitioner that way. All right, I'll show you this. Good, sounds good to you? Right. So it's the duty of partitioner to take a call which key goes to which bucket, and hence which key goes to which reducer is the call of the partitioner. All right, next is that the MapReduce, the whole logic is actually very similar to group by clause of databases. Just that it's far more flexible, because in case of SQL, you can only use those constructs which are part of the SQL. Here you can use the construct provided by a real programming language. So you can see that if you remember the group by clause in SQL, what is group by? Group by takes a table, orders the data and groups the data based on a column, and then apply an aggregation over all the values for that group. right? That's exactly MapReduce. While map decides what is the criteria on which the data needs to be grouped, while and the reduce decides how to aggregate values. Okay, so select word comma count star from a table group by word. That's what is, you can see that that is essentially SQL way of saying our word count map reduce. Make sense to everybody? All right. Now the way when we say SQL, right? When we say that this is my SQL and is going to do something, here we are not dictating how should data be sorted and how should on which machines and whatnot. Similarly, in case of MapReduce also, we do not state how how should the data be sorted. We leave it to the framework. We leave it to the framework to get the internal things done at its own. Okay, is the analogy clear to everyone? Yes. All right. Great, great. Now, we will take one example before we jump to the questions. Okay. And then first we will take an example and then we will try to understand what is streaming and then we'll solve these four problems. Okay. All right. Let me take, this was a word count example. It is clear to everyone. All right. Now I'm going to take you to the data sets. Let me go to the file browser, data, and then in the data there is one file called this. Okay, it's a users.dat. So basically, what is this data? Let me explain to you. Is the movie rating given by a million people to various movies? Okay, if you go to movies, what are the movies? So this file contains the relationship between movie ID and the movie name. Okay, it's in the plain text. So you can see that one is given to Toy Story and it was released in 1995. Okay, it is an animation, it's a children's movie, it's a comedy. And then two means Jumanji and so on. Okay, so here it's looking a little awkward. Let me go back to my CloudX lab. So those who are not aware, in case you logged in into LMS, you're also logged in into CloudX Lab automatically. Okay, so that's the kind of trick we have done. So I'm going to open the console and copy to clipboard. Okay, I'm increasing the font a little bit so that everybody can see. All right, Hadoop fs minus ls slash data slash ml 1 million. I think that's the folder name. Good. Now here, if you, so I'm interacting with HDFS from the command line. Okay, I'm saying 1 million and then movies.dat. Okay. So Raul, are you? I missed your question earlier regarding Hadoop FS minus LS. Okay, so basically, we when we say Hadoop fs minus ls, we are talking to Hadoop and asking for the list of files. We are talking to HDFS asking for a list of files. Okay, is it clear now? If you do not provide a directory name, it basically picks your home folder. Every user, just like in Windows, you have a home folder containing documents and everything. Unix also provides the same home folder to every user. And similarly, HDFS also provides a home folder. So when you do not provide a directory on Hadoop FS minus ls, it picks up the directory from your home folder. So right now we are going to talk about this data. Okay, so it contains four files. One is movies.data, that this one. It contains the information about movies. Okay, I'll show you. I'm using pipe more. It's a Unix command for the paging. Okay, so here you can see that the movie ID 1 means Toy Story. It's an animation, children's, and then comedy. These are the genres of a movie. Okay, you can use this data actually, and then you have ratings.dat. Okay, now okay, you can see that the ratings of that here is the first user has voted for this 1193 movie 5 at this particular time. Okay, first user has rated for this movie this much at this time. Okay, so now, so in the ratings.dat, I'll just take some sample here. So ratings.dat, this is the data. Okay, so here the data is user, movie, rating, and time stamp. When did the user rated the movie? Okay, this is what it looks like. All right, so our input file is clear to everyone that this is our input file, right? Now the objective is find average rating of every movie. Okay, find average rating of every movie. So what will mapper do? Anybody? Okay, so mapper will get this line in ones because this is the input file. So since it's a text file, we will get one line at a time to our mapper. So what should mapper do? Anybody? Just in the plain English. We want to find out. So this is our data. It contains the user ID, movie ID, rating given by this user, and at what time did it do. Now question is, what if we want to find out the average rating of every movie? Okay, so what will so this mapper function would get would okay, let's say line is the input data. Okay, or you can say, let's say we have function my movie mapper, and it's getting a line, okay, in the argument. Now Now, how do we find the average rating using SQL? If this data, if this data was in say Microsoft SQL, or in a database table, what will you do? You will say select movie ID, comma, average rating from from ratings group by movie ID, right? So if we have to do the same thing using MapReduce, how will we do? What will our mapper? What kind of key values should mapper output, and what will the reducer aggregate? Yes. Let me take out your questions and then try to aggregate your answers. Good, good, Samip. Good, Ravichandran. So, your mapper will basically, some of you have answered correctly. So, your mapper will basically say, I'm trying to be very user ID, comma, movie ID, comma, rating, comma, time equals line dot split based on double colon. Okay, and then our this code will essentially say emit. There is no loop as such. It's saying emit movie ID, comma, rating. Correct? And in the function called my, what do you say, reducer. Okay, my, let's say, my reducer AVG we call it, because it'll get movie ID, okay, comma, array of ratings is an argument. Now what will it do? It will essentially, all it will do is it'll return average of array of ratings. That's all. Sounds good? So this way, the result we will get is the movie ID and the average. Is everybody clear about this problem? No? Feel free to ask if you want me to repeat. I'm completely okay with that. So Anil's question is, so number of movies is equal to array length no, actually. Number of ratings per movie is the array length. Okay? This will be called number of movies. It will be called as many times as there are movies. Okay? While this will be called equal to number of ratings. Okay, basically my movie mapper will be executed against every line in this file. Okay, and while after it has been, groups are generated. So because we are emitting here, we are producing our movie map, our mapper is giving out key as movie ID and the rating. So Hadoop will take or collect all of the results of execution and order that and group by movie ID And once that is done, it'll, it'll contain the total records, which after grouping would be equal to the number of movies. So our reducer function get executed once per movie. Make sense to you, Anil? Yes, that's right, Samip. It's discarding. Our emit is only because we don't need other stuff. We don't need other stuff right now. We don't need we don't need user ID and the time. Therefore, we are discarding everything. All right? Great, great. Any questions at this point? I'm talking very theoretical right now. We will go into the actual implementation because here the important part to understand is how do we break down our problems into the we want to figure out we want to convert our problems into MapReduce. Okay. Now a quick question to everyone. Next question I need to ask is count of. Okay, good question, Raul. Raul's question is what happens when, let's say, a particular line has different delimiters. In those cases, this particular split will not result in four values and will give an error. Those kind of error handling need to be done as part of your code. You need to detect is does it contain this splitter or some other splitter. Okay, that much knowledge you need to have about your data. Good question. All right, now let's say we want to find out how many movies released or how many movies were rated every year. Yes, so the last column contains the time since epoch. Epoch means 1st January 1980. Okay. Since then, how many milliseconds have passed? Okay. For example, this one, there is a command in Unix to convert epoch to, how do you convert this? Okay. Date minus minus help. Okay. How do you minus D? Mhm. Okay. So anyway, let me just show you. In Mac, this is how I do that, minus R. So you can see that this particular rating was done on 1st January of 2001. Okay, at this time 04. So this is a timestamp in milliseconds. And this one you can see, okay, this one also has been done on 2001. All right, so you can see that clearly that this data has quite useful information about every movie. So let's say we want to find out how many movies were rated every year. What will you do? Pavan says mapper will contain year out of the timestamp and one. Good, good. Ravichandran says rating and but we don't want to count the average. We want to basically how many total ratings will be released. Good, great. So let me again copy the same thing. Okay, so here we will say, let's say there is a function called parse time, and we say, let this is our date. Okay, I'm just writing some pseudocode, and here I'm just saying 1. Good. All right. Let's say I'm just calling this another function. It'll be year and array of ones. Correct? Now, what I'm going to do is I'm just going to either count or sum, return this. I'm going to just say dot length. Okay? Because length is also equal to sum in case of ones. Is everybody with me? That's right, Pawan. Sum will be useful if you use combiner. That will come back to it again. But right now, it's a single reducer. All right. Is everybody clear, or are you getting intimidated by the kind of code I'm writing here? Or you are disgusted by the code I'm writing here? Because it's really, really non-functional code. All right. Is everybody with me in this? Okay. Rol's question is, could one of these be these codes implemented in Web Console to get better visualization? Yes, they can be. Okay, I'll show you in a minute after a while. I'll show you now all of this. So Akash's question is, how do we implement these codes in SDFS? I'll show you. That's what is the next assignment. So right now I'm talking general theory, and then we'll get down to doing the actual MapReduce. Okay? The overall idea that we are trying to do is that we get used to breaking down any logic into MapReduce, and then everything will be very easy for us. Okay. Now there are four, five questions that we had discussed earlier. First question was, for counting the frequencies of letters. Frequencies of the letters are generally used to decipher many things about a text. Okay. So the frequency of letters, one is quickly used to detect whether a particular text is in English, French, Spanish, Hindi, Tamil, or any other language. Okay, so frequency of letter is very important, and frequency of letter generally represents that in which era a particular text was written. Okay, and similarly, frequency of words is also used as a predictor of the time in which it was written. All right. So question is, do we require MapReduce in case of frequency of letters? Second question is, you don't have to answer right now. We will go through it, or let's go through it later on. I think these questions I have to anyway go through. So we'll go through these questions later on. For now, let's move ahead with the real implementations. Okay. All right. Now, before we will like to show you using the most simple way, which is something called streaming job. Okay, we will try to show you the map reduce the word count using something called a streaming library. Okay. All right. Okay. So as we said that MapReduce was written in Java. So main MapReduce is written in mainly in Java, and we will cover Java later. Why? Because when Java comes into play, the learning becomes little too congested. Okay, you will see that we have to use Eclipse and then we have to compile it, upload the jar, and the whole process. So instead of focusing on MapReduce, we get focused completely on Java. Okay, so we'll use something called a Hadoop streaming library for now, and then use MapReduce in Java. And we go into more and more details in Java at later point of time. Okay, so when Hadoop guys realize that not everybody is likes so much of Java, and Java takes a little bit more time to get something done, they came up with streaming job. Streaming job makes it possible to use any programming unit, as in any program, to be used as mapper and reducer. Okay, you just pass the name of the command as the argument, and then as the it'll use that as the mapper or reducer. Okay, so it's a library which makes it possible to use any binary or any program for that matter as mapper or reducer. Mapper, the only difference is reducer does not get data which is grouped. For some reason, for some reason, they basically ungrouped the data that reducer is supposed to receive. Okay, so in the streaming, reducer gets sorted data but not grouped data. That's the difference between the standard one, but that's not too much of deal breaker. You will see that quickly, and you will see that why it's so important, because in Unix command line it's easier to handle the data which is not grouped and is generally in the tabular format. Okay, that's one of the reasons why streaming job ungroups the data. So Hadoop sorts the data, groups the data, and then this library called streaming job ungroups the data. So what is streaming job? Streaming job itself is a MapReduce program which calls the external commands provided to it. It's as simple as that. Okay, so the way we execute Hadoop streaming is this way. In case you are on a new system in an organization, what you can do is first find out where is this Hadoop dash streaming located. Okay, first find out where is this file located. So how do you find out? You basically say find slash minus name and this file, and also send to, which is error stream, to dev null, meaning remove all the errors, ignore all the errors, and show us only the output. See that? Okay, this is the way. Whether you are on Cloudera, Hortonworks, MapR, you can always find the library this way. Next is, so generally this is also pointing to the same location. Let's just see if it is there. Also note that this jar file the logic that this is generally located in the local file system, not HDFS. This is not located in HDFS. So your Hadoop, okay, so let me take a step back and try to explain what does it mean by this command. Okay. We will go to the MapReduce later. Let me just explain the basics. All right, here we go. So the way you execute any program in MapReduce is generally in the classic case where you are writing Java code and all, you first code everything in Eclipse, create or howsoever you code it, whether Eclipse, IntelliJ or simply VI or whatever you want. So you create your Java program, you compile it and bundle it in jar, then hand it over to Hadoop jar. Okay. Similarly, right now, instead of our code, we are handing over this bundle of code called streaming jar, streaming library. So streaming library is a MapReduce code itself, okay, which calls the external program. It's like a Trojan horse which will call other things from outside. Similarly, not Trojan horse in negative sense, but in a sense that it's a caller. So streaming jar makes it possible to run any external program. Right now we are going to run our Unix command. Okay. So let's try to understand in parts. Here, the first argument which we are going to provide, we are saying Hadoop jar and we are providing a streaming jars library. This library is going to get executed by Hadoop in the and will this jar contains inside its own MapReduce, which are calling the external commands. Okay, so now here we go. All right, now here we are saying the input is located in this place, which is HDFS, and save our output here. Okay, and when we do not provide a path which is starting with slash, it means it's a relative path, which means this folder would be created with respect to your home folder in HDFS. And then the next argument is the mapper command, and now this looks little cryptic. What is it? It's nothing but a command that can do the find and replace for you. It's replacing space with new line. It's removing space and substituting it with new line. Okay, and then unique minus C is doing the unique for you. Okay, I'll show you something. All right, let's try to see what does this command do. Okay, let me go to my web console. All right, here is my web console. It's a little too big font, so okay, so cat big.txt, or let me just take a section of this file, tail big.txt. I'll say head. Okay, so head big.txt, what does it do? It basically prints first few lines. Okay, so this command sed, we are piping the text, the first 10 lines of big.txt to sed. What does it do? Okay, or let me just try to see if I can. Yeah, so head -1 basically gives a single line. Okay, so you can see, okay, hash means I've commented the rest of the line, which means head -1 big.txt has printed the first line. Now when you pass this line to sed, what it does is it replaces spaces with new line. So your new line is the good. So basically sed has converted the input data into key value where first key is the and value is null. Key is project, value is null, and so on. We will go into more details. So essentially what I'm trying to display is SED minus this means substitute space with new line. Okay, and G means globally does not stop at the first space. If there are 20 uh, 20 what do you say, you can see that if I don't provide G, it basically replaces the first space and does not move ahead. Okay, so all right, so that's the role of SED. SED converts a line into one word per line. Okay, a sentence per line into one word per line. And then there is something called unique. You see unique here? Unique minus C counts the occurrences of something. Okay, I'll try to show its use case. When I say echo hello, semicolon echo hello, okay, it prints hello twice. Okay, and you can see that. Now if I pass this, as in I I pass this. So in Unix shell, you can put round brackets so that it becomes a single command. You can pass it to unique minus C. You can see that it has counted hello as 2. Okay. Now imagine that echo hello. Okay. Here it has not counted correctly because unique minus C expects data to be ordered. Okay. So So you can see that echo hello, hello, hello is basically printing hello thrice, but one of the hello is only containing L. And when we pass it to unique, it doesn't function correctly. Reason is unique minus C expects the data to be ordered. Okay. So this is to clarify that the data is being sorted by Hadoop, not by unique. Okay, unique does not function correctly if the data is not sorted correctly. So output of SED, which is one word per line, is ordered by Hadoop via Hadoop streaming, and then the result is passed to reducer by using unique minus C, and the data is converted into unique. So let's say your input data was sa, re, saga. It'll get converted to sa, re, saga. And then that data will be converted into unique. Basically, since it's ordered, unique minus C counts the frequencies in that data. Similarly, had it been on many machines, okay, it would function in this way. Had it been multiple reducers, you will get still the correct result, just that some part on one, some part on another, and some part. The important part to note is even if there are many reducers, it is guaranteed that same key will land on same reducer. It will never happen one SA went to one node and other SA went here. No. It is guaranteed that the same key goes to the same node. Okay? Unless you have implemented some of your custom partitioner and forcing it to do the mistake. Alright? So this is exactly what's happening. So SED is converting into A, and internally this data is interpreted by Hadoop streaming as key is A and value is null, key is B, value is null, and so on. And Hadoop internally is sorting it, bringing down the nulls together, and then unique minus C is basically counted the occurrence of the keys that many times. Okay, is everybody clear about this example? All right, let me take a step back. Now, one of the questions that is generally asked at this point is, what is it that mapper is supposed to give out? Mapper is supposed to give out key value pair separated by tab. Mapper is, if mapper tries to not give tab as the out in the between key and the value, then whole line will be considered as the key. If mapper gives out multiple tabs, only first tab will be counted and second tab will be counted as part of the value. Okay, only first tab, its data is separated by the first tab, and the value before the first tab is key, and value after the first tab, everything is the value. Okay, all the data after the first tab is a value. Okay, so mapper, whatever command is it is supposed to give key tab value. And also please note that you can configure whether it's a tab that you want, or it's semicolon, it's a colon, or a comma. It's up to you. Okay, it's up to you how you want to tackle it. Okay, how you want your mapper's output to be understood by Hadoop. Okay, by default it's a tab. You can configure it to something else. Now, reducer will get ungrouped but sorted data where key and the value will be separated by the tab. Okay, so is it good? Should we try to execute it now? Let's try to execute. Okay, and here this is our streaming library. This is our input data mr word count input. Let's take a look at it. Let's take a look at it. And where is my hue? Okay, Hadoop fs minus ls data mr word count and input. Okay, you can see that we are providing the folder name that contains a single text file. Okay, so let's try to execute the command. Okay, so let me just copy it and then see what happens. Also, let me change the output folder. Okay, so Hadoop jar user, this is fine. Input is okay. Output, I'll say word count on 18 June in my home folder. Today is 18, right? Okay. All right. There is something wrong with copy pasting, but that's okay. So it says that this is the URL to track. When you get this kind of error saying the site cannot be reached, you put it here c.cloudxlab.com. Okay. So this is the status. I'm running the MapReduce job right now. Internally, it's saying that there are 2 maps and 1 reduces, and there has been 0 failed, 0 killed, and 2 successful, 1 successful, meaning everything is successful. Okay, so yes, that you can use using HDFS, HDFS FSCK. Okay, you can see that in the big.txt. All right. So it has also printed a lot of statistics. Here it shows that it is finishing first the map, then the map, then the map, and then it has finished the reduce. You can see that. And then it is showing how much time it took to read and written, and there how much time it took for maps and reduces, and so on. Okay. This way you will know exactly what's going on. Okay. Josephine, which question are we talking? Do you mean the input data here we have provided? Here we are saying Hadoop jar, this is the jar file. This is the part of the standard Hadoop library. Whether any distribution you're using, they have a streaming. This is the input folder, and this is the output folder. This is the command we are passing. Okay. This is the input folder. You can check what's there in the input folder. This is the input folder. We are saying minus input space the location of the input directory. Okay. So Anil's question is how to get streaming jar on machine. It's already installed on all the node. Which machine do you want to put it on? It's part of the standard distribution and is already installed on all machines. If you are using a VirtualBox instead of CloudX Lab, it would be there by default. It is just that you might have to use find slash minus name Hadoop dash streaming dot jar to dev null. Okay. All right. So now let's take a look at the output. All right. The output is saved in this directory. So we can say Hadoop fs minus ls, this directory. Now you can see that here there are two files. One is called success and other is called this. Success is an empty file. It marks the status that, hey, the output is done. Okay. This file generally means that the MapReduce has finished. And this is the file that contains data. So we could say Hadoop fs minus cat and more. You can see that this is the output. Okay, so this is the word count. It, everybody on the same page? All right. Rolf's question is that could you ping the command? So this command should give you the information about I'll just give you this command. Okay, this command should give you the information about all the data blocks. All right, for me it shows that these many replications and everything. It's a read-only folder for you. Okay, and you can see that these are the blocks. All right, great. Now, are you happy with this result? Are you happy? This is the word count. First column contains the number and second column contains the word. You can see that. this. Here, one means this double quote is part of the word. Okay, double quote is part of for. Are you happy with this? No? Correct. We need to clean this data. And how do we clean this data? Now, which means we'll have to, our work will not happen in a single command. We will have to write a kind of code. We cannot, we'll need to write it won't happen in a single command. Therefore, we'll have to write the script. Okay. So now let's say we write our script in shell. We can write the same script. Anything that can execute on the shell can execute on Hadoop. Okay. Now let's try to create a file. Okay. I'll show you. I've already created the same file. Okay. It's called mycmd.sh. Okay. I'll open it in Nano. Nano is an editor for editing the files. So here there is few things you can see. It's a file. mycmd.sh is a file. It's a kind of a shell script. It's a kind of a program. And what is a shell script? You basically write all the commands, one command per line, and save it in a sequence. Okay. So this is, so we all we did was we wrote a nice program, and this is a nice program as in first we replace space and tab and as many of them as there are in a line with /n. Meaning if there are two spaces, three spaces, tabs, everything combined together get replaced with a /n. So any white space, this means any white space gets continuous, any continuous white space, meaning space or tab, one or more of those. Okay, meaning continuous white space get replaced with single line. Next is we replace anything which is not number or which is not alphabetic character with nothing. Okay, next thing we do is we translate a to z into small a to z, meaning we are converting the data into lowercase. Okay, let's take a look whether it works or not. So first of all, once you create your program, you should make it executable by saying chmod +x. Okay, if your program is not executable in Unix, it will never execute on the other nodes. Second, you should always test without Hadoop. Say, I want to test it, so I'm going to write some garble and say I'll write this, or let me try to say, uh, what was that head command? This one, right? So I'm going to pass the output of the first line, okay, or maybe say 2 lines. This is not good. I need some special characters. Okay, so there are brackets, hash, and other things. So they should be removed. There are dots. Okay, so when I say my here /mycmd, / means it's in the current directory. Dot means current directory. You can see that it has converted into lowercase and removed special cases, special characters. Anything which is not alphanumeric, whether it was hash or it was dot, it has been removed. See that? Okay. So mycmd.sh is the one who is able to clean the data. All right. Now, counting, we don't need anything special. So we can actually test our command by using sort, because the Hadoop essentially is behaving like a sorter. You can see that Arthur has occurred twice, B has occurred twice, and so on in these 10 lines. All right. Now you can see that result of reduce is not sorted. Okay, result of a reduce is not sorted, and you don't need to sort it. Good. All right, now let's try to execute this over the cluster. Okay, and here is the format. So Hadoop jar and streaming jar, we are passing exactly in the same manner. I'll just replace this with current, and then here we can specify how many reducers do we want. Do we want two or do we want one? Okay, in this case we are saying two. Next is the input folder. We're providing input folder same as the previous one. Output folder, okay, we could say what should we say, June 18. Okay, and then here is the mapper and here's the reducer. Okay, the most important difference here we will notice is this command. What does it do? What does minus file mycmd.sh do? Okay, what exactly does it do? My question to all of you is SCD available on all nodes? Is SCD available on all nodes? Yes. The SCD command available on all nodes? Yes, right? Is unique command available on all nodes? Correct, yes, right? But is mycmd.sh available on all nodes? Correct. That is the reason we need to ship this command. We need to ship this file, which is going to behave like a command or a program. We need to send it to all nodes. And that's why we need to say minus file. Hadoop MapReduce comes with a facility called distributed cache. This distributed cache is essentially for smaller data that you need to ship along with your Java program. Your jar file that you are going to execute or the program that you want to send to everywhere need to be put into something called distributed cache. Distributed cache is nothing but a small disk space provided by Hadoop before and it's copied along with your program. Just like when you have a mobile app has something called resources bundled with it. Whether you're coming from C Sharp or .NET or you are coming from Java background, this idea of something called resources that you bundle along with your program. Distributed cache is that. You bundle your stuff with your program, bundle the data, not only the code in your Hadoop, in your MapReduce. So this file is kept in the distributed cache and is made available on every node. Question from Pavan is, what if reducer was also I'm trying to enhance your question, Pavan. So what if reducer was also an external program written by us? In that case, how should it look like? In that case, let's say we are having here slash my reducer dot sh, or say this is a Python program. We write it in Python, make it executable. First line should contain the proper information about the program name. You can see that in our you can see that my cmd.sh contains first line. You can see the first line. I'm not sure you are able to see it. Let me open it in something. Okay, so you can see the first line after hash exclamation. It's the name of the program that defines how should this code be executed. This is the way Unix identifies how to execute a program automatically. Okay, in Windows, generally when you double click on a file, which program is used for executing that is decided based on the file extension. In case of Unix, it's the first line of the program that decides how rest of the program needs to be executed. Okay, so once you have made your program executable, let's say you wrote my red.py, first line is hash exclamation user bin python, and your program is perfectly working on the console. Now you want to test it on the actual cluster, so you will say file my red.py. There'll be multiple file syntaxes. Okay, there'll be multiple file syntaxes. Okay, good, good. Another question is, in this example, had we used Java, do we pass MapReduce code at jar file? Yes. Had you been coding in Java, you'll bundle everything in jar file. Instead of using this jar, you will use your own jar. And the argument, whatever you pass it here, will be given to your program instead of Hadoop streaming. Okay, it'll be up to your program what to do with the arguments here. Question from Anil is, can we save script file to HDFS and use it in MapReducer? Answer is no. Okay, whether it's jar, this one, or these files, they have to be local on that machine. Yes, that's correct, Pavan. Thank you. All right, great. Let me explain again. What was the point? Okay, so yeah, if you have your Unix program you are trying to execute, in that case, if there are reducer is also some external file, you will say minus file my reducer.py, or say you have C code which is you compile, you will say that compile name, or if you if you remember a.out, or if whatever is your file name, you will mention it here minus file. Okay, so in case you are writing in Java, this jar file will be replaced with your own jar file. Don't worry, we will come back to it again. Okay, so before that, let's execute our program. Okay, before executing, we have to make sure that whole program is either in the single line or it's in here. Okay, here we go. So it says it's not a valid jar. Did we make a mistake? Let's try to see. What was the jar file name earlier from the earlier page? Let's just copy that one because that seemed to work fine. Okay, all right. Let's try with this if that works. The slashes are the slashes which I put here is to make sure that we can write the command in the multiple lines. Josephine, was I able to answer your question? Okay, all right. Here we go. So we're going to go to the console. Here we are saying this. So when you have a big command spread over multiple line, you end a command and each line with slash. Okay. That way you can write a command on multiple lines. You can see now you can see that it's basically executing it. And once it's done, it'll store the output in clean underscore June 18. Alright, so we can see Hadoop fs minus ls. Okay, so now you can see that there are two parts. Why? Because this time we are using two reducers. Okay, let's say Hadoop fs minus cat. You can see that. Okay. All right. Now you can see that although the keys are unique, as in each file, one key will not go into the two files, part 0 and part 1. It will only go to one file. Okay, because each file represents the output of each reducer, and one key does not go to two reducers. But there is a round robin. It's not. If you try to concatenate part 0 and part 1, the output will not be ordered, while individually part 0 and part 1 are ordered, but the ranges in both are overlapping. Therefore, when you concatenate part 0 and part 1, you will not get the correct results. Take a look at the output. I'm also passing the command here in the console. You can save this. Sorry. Yeah. You can save this and then try to execute. All right. So today we try to run our streaming job and try to basically solve the problem of MapReduce using the shell command. All right. So Rol's question is, so what happens if we want to see the data in one file? Generally, what we do is we will use our partitioner carefully, okay, such that all the words starting with say J and above go to the second reducer, and all the words starting with A till J go to one file. Okay, that way we can make sure that just by concatenating we get the correct results. If we do not provide partitioner, the one that's used is the hash code based. Every word's hash code is computed, divided by number of reducers you have, and based on that, a reducer is chosen. Okay? If hash code is 15 and there are two reducers, you will get the second one and so on. Okay? So hash code is generally a big number and reducers are generally 2 or 3 or 5 or 6. Okay? So when you have to fit the big number on a small number of reducers, you generally find the remainder. It's equivalent to rolling a tape as in inchy tape, the one which is used for mayor, on a small, what do you say, a small stick. Okay. All right. Okay. When running a jar, if you are using, so you generally either provide the full class not found. Can you show the command, Ajay? We'll solve it right away. Or let's try to, all of you, please try to execute the streaming command and we will try to execute it and try to see if you are able to get it done. Okay, so his is frequency finder.jar. So generally this is you, what you do is you use a variable called class path. Okay, and whatever is the default class path, then put in the folder. Okay, wherever your my lib is there. Okay, where is this file located? Are you able to find it? Can you try to use find slash name frequency finder to dev null? Are you able to find it? So you use, in case it's in your home folder, you use dot slash. Okay, or the other way is instead of saying mylib, you say this. Okay, that means it will search for the jar in the home folder. Generally, this is the right way. You provide the actual location of the jar file. Okay, this one should work. All right. All right. See you tomorrow, and try running these two commands by yourself. Okay. Also attempt to try to attempt all those four problems we are going to go. Okay. Just drop me an email, Ajay. We will try to rectify the problem. All right? No worries. All right. Thank you, everyone. Have a great week ahead. I'm happy to have a great class. And all right. And feel free to ask questions, coordinate with your classmates using the Facebook group. Okay. Looks like everybody's on Facebook, so people can use it. Okay. Bye bye. See you tomorrow.